For this example, we're looking at a structure which is made up of beams AC and CD. We have a point load, which is acting at the midpoint between A and C. We have a constant line load force between C and D. We want to come up with the shear force and bending moment diagram for that structure. We're going to do what we will do throughout, and we're going to do our external reactions first, external force analysis, reactions, and then from that we'll go in and calculate what shear force and bending moment is along that structure. Being we got two pieces here, I'm going to draw a free body diagram of each one. So this is AC and this is CD. I'm going to put Y positive up, X to the right. I'm going to have AY as being my reaction force there at A. There's a pin joint there at C, so there's a single force there. And then, of course, there's the applied 6 kip force there at B. From Newton's second law, we know we have an equal and opposite force there at C. We have a reaction force at the wall there of dy, bending couple there of md, and since we have this constant line load there, we're going to have the 20 kip force there at the midpoint between C and B. So what I'm going to do is first use equilibrium for member AC. I'm going to do a moment equation about point C. So that's going to be the 6 kip force. It's got a moment arm of 4. It's a plus sign because it's in a plus K. I've got AY. It's got a moment arm of 8. And it's going to be in the negative K, so I put a negative sign there. And so therefore from this equation then I get that the reaction force at A is 3 kips. If I do a summation of forces in Y, I've got AY plus CY minus 6 for equilibrium. That's a 0. So the reaction force there at C is going to be CY is also 3 kips. I'll look at member CD, and my first equation is going to be summing forces on that member in Y. We got minus CY, got plus DY, minus 20. For equilibrium, that is a 0. So the reaction there at the wall, the reaction force, is going to be 23 kips. Do a moment. It looks like here I'm choosing to do a moment about ND. So that's going to be the 20. It's got a moment arm of 5 with a plus SIGN sign. I've got CY. It's got a moment arm of 10. It also is a plus sign. And then the couple to the wall MD. Together that sums up to be a 0. So the wall is putting a couple of minus 130 kip feet on there. So this gives us our reactions. So now I'm going to jump in and do the shear force bending moment diagrams. But to this end, what I'm going to be doing is looking at the structure as a whole. So let me draw the whole thing here and repeat what I already know. And that is I have this reaction force of AY. We've got a number for that from above. I've got the applied point load there is 6. I have the constant load there, line load, which is acting between C and D, and then I have the reaction force dy and md. And so this here, I'll call that P of X or something like that. How about that? Okay, so I'm going to base all my calculations on this structure as a whole. And as I look at shear force, I'm going to start from the left and work to the right. So at the left hand side, VO, I have this force there of AY. And keep in mind that our sign convention for shear force on the left face is positive up. AY is shown as positive up, so that gets a plus sign. And AY we saw was equal to 3 kips. The shear force there immediately to the left of where the point load is applied is going to be equal to VO, or I'm sorry, V at the left-hand side, plus the area under the line load between A and B, which there is none. So that remains a 3 kips. As I move across that point load, though, I'll use our jump equation. That 4 plus is equal to 4 minus plus the point load, and that since that's a down, that's going to be a minus 6. So I have a minus 3 kips. So the jump down there of minus 6. I say I'm interested in the shear force at C, which is at x equal to 8. So that's going to be what it is immediately to the right of that point load. And then since there is no line load between B and C, that remains minus 3 kips there at 8. And then if I move all the way over to the right hand side, x equal to 18, V is what it is at 8 plus the integral from that would be from x equal to 8 up to 18 of P of x. Well, P of x is a constant and it's downward, so the area under that curve then is going to be the minus 2, because that's the line load down. It's acting over 10, so in the end what I have here is minus 23 kips. Minus 23 kips. So let me make a sketch of V. We know that V starts out here at 3. It's a constant all the way across, so this is 3. There's a jump there at B, a jump down of 6, so that's going to be a minus 3. It's constant across, and then it goes down to a minus 23. Over there on the right hand side. So here's how the shear force looks. We'll like that. Now basically what we do is do an integral under the V of x curve to get M. But let's do that step by step. So for bending moment, we'll start there at the left hand side. And on the left hand side we saw the M of 0. Well, there it's a free end, so M of 0 is a 0. Where the point load is applied, that's equal to what it is on the left end. And then of course we integrate V of x between 0 and 4. Again, M of 0 is a 0. Since V is a constant across there, it's 3. The constant times the distance there, 4. So M at B there is equal to 12 kip feet. If I want to know what the bending moment is there at 8, I take what it is at 4, and then that goes the integral of 4 up to 8 of V of x dx. Well, we saw M at 4 was a 12. V of x we saw was a minus 3. It acts over a length there of 4, and it's a 0. And then finally, when I calculate the bending moment on the right hand side, that's going to be M at 8 plus the integral from 8 to 18 of V of x dx, like that. M of 8 again was a 0. And if I go from 8 to 18, we said V is a linear function of x, and its base is 10. So 1/2 base times the height. The height there is minus 23 minus 3, like that. So that gives us a bending moment there of minus 130 kip feet, like that. And that checks out. C above for our reactions. So we end up with checks. I guess one point I failed to make there on the shear force was we found that the shear force on the right side was minus 23. And that's exactly what we got there for dy. We got dy was 23. But since the right face positive is down and dy was up, that's how we get that negative sign there. So the shear force bending moment diagram agree with what we got from our equilibrium analysis, as it should. One thing to note here as we get ready to make this sketch is that for the range of x between 8 and 18, m of x has an increasingly negative slope. How do I know that? Because recall that v of x is equal to dm dx. And if you look back at the equation for v, it's a negative slope linear function, which means again that the slope of m is getting more negative as we move across. It's going to be parabolic, and it's going to be such that the slope is getting more negative. So let me scroll back up here. We know that v of x started out as a 0. We know that it went up to a value of 12 over a straight line, because keep in mind that v is equal to dm dx. And then again, this was at 12. We saw there at point C, at that pin joint, the bending moment is a 0. And so let me do a better job. That is a straight line here. And then immediately to the right, it's going to be a function which is quadratic, and the slope is getting more negative as we go. So as you draw it in, make it look like that. Really hard to draw this to scale here, but it says that over on the right hand side, the bending moment is minus 130. So this is a quadratic function. We didn't have to derive that function, but we know it's quadratic because it's the integral of a linear function in x. So all we needed to know what it is here, we needed to know what it is there, and keeping in mind it's going as it is because the slope is getting more negative as you move across. So in review here, we did our usual equilibrium analysis. We actually broke the structure into two parts to easily get our reactions. But once we had that done, we put it all back together and we looked at the structure here as a whole. And I just moved from left to right and used three fundamental equations. One is the area under the line load gives us the shear force. Secondly, for a point load, we have a jump up or jump down depending upon whether that point load points up or down. And then the third equation was, we said that the integral of the shear force gave us a moment. We didn't really do any integrations any more than we just simply looked at our functions and knew what the area was under the curves, and that's all we needed to know in order to get our values for v and m at those locations.